Okay, so our next speaker is Retore, and she's going to talk about Temperley-Lieb algebras and their applications to integrable spin chains, right?
Yeah, so thank you very much for the opportunity to give this talk here. I'm very happy to be back to IDD, and it's my first time in Wrocław, and it's really nice. Yeah, thank you very much. So I'll talk about this type of like dynamical Temperley-Lieb related to this ZK Orbifold Hamiltonians. And this is a work in progress with Rob Kobbers, Eli Pomoni, Paul Ryan, and Kostas Zubus, and all of them except Eli are here. So you can also ask some questions to them if you'd like. So the motivation is the first motivation is the same as many of the talks here, which is going a bit away of having a lot of symmetry, so having a bit less symmetry and see. And then more importantly, seeing how much of these available tools that we had when we had all the symmetry we can still use in a certain way. So the plan for the talk is a review very quickly these orbifold theories. In particular, I will focus on Z2 for the first part of the talk. And then I will make a claim about something on these orbifold theories. And to be able to explain it, I will like have a pause and explain a little bit what are these Temperley algebras in the standard case, which is usually related to XXZ, for example. And then I'll introduce the dynamical version of them. And if I have time at the end, I will relate to the XXZ chain in a quite interesting way, which following Paul, it will be related to twists as well. So the Z2 orbifold case, like basically you start when n equals 4 superring mills with a gauge group SU2n. And let's focus on fields X, Y, and Z. So what you do is basically you conjugate your fields by this gamma, which has this 1 and minus 1 here. And you also put this overall coefficient here that depending if your field is a Z, an X, or a Y, it behaves differently. And for the Z2 case, you can see that both X and Y lead to a minus 1 here in front. So they behave kind of in the same way, while the Z behaves a bit differently. So in practice, what happens is that we always end up like with a Z that's diagonal and like some off-diagonal X and Ys. And what this is, okay. So what's happening in practice is that the SU2n is getting broken to SUN times SUN. And we will call like the first copy 1 and the second 2. And the fields will now behave like this. So basically the Z1 transforms in the adjoint of the first copy, the Z2 in the adjoint of the second copy, but the X and Y behave in the are in the bifundamental of these two copies. And in particular for the talk, I will focus on the XZ sector. So this is the quiver. So basically I'll have only Z's and X. And one extra thing we can do is marginally deform and having like 2 different couplings instead of having all the same coupling. So, and for the whole talk, you only see again a G at the very end. I will use this kappa, which is the ratio of the 2. So what happens? So for this XZ sector, the fact that you broke a part of the symmetry and you have now this new structure, one of the consequences that not every state is allowed anymore. So now you have, like, for example, this state has nice contraction, so everyone is contracted properly. And like if you end here with a 2, you have a 2 starting in the next one. But this one is not allowed because you have like X1, 2, but the next one is a Z1, so this is not contracted properly. So you basically have to like just do the nice contractions. The other thing that happens is that if you compute the one loop Hamiltonian, like in n equals 4 superring mills, we had that for the SU2 sector, this was basically the XXX spin chain, which is integrable, and it was a nearest neighbor Hamiltonian. So again, and we heard about that both from Saskia and Paul also. And this one loop Hamiltonian here is also nearest neighbor, But something changes. So now we have like two copies, one associated to the index 1 and one associated to the index 2. And the Hamiltonian is basically the sum of these two. And they are related just by kappa going to 1 over kappa. And if you put kappa going to 1, this is called the Orbifold point. And this is fully integrable. The case with kappa equals to 1 is fully integrable. You have basically SU2, like two SU2s. And so that case is very nice. But this case is also very nice, but it behaves it looks like you didn't change much, but the behavior is very different. In particular, yeah, there was a lot of work on these. I wrote some here on the board. The first one's by Ellie and Gadian Rastelli. And there are also very nice works also with Costas and Rab and Bartel and Zhang. And then the last 2 years, there was some type of Batansatz that's kind of long range done by Denise, Juan Miguel, and Ellie. And then in the second one, also Kang. And so there are some works on this, but we would like to approach this question in a slightly different way, trying to use a different structure that appears on this model. So okay, I forgot to say, but there are two vacuum. Like when you have like the n equals 4 superring mills, X and Z behave basically in the same way. But here, one of them is like in the adjoint, and the other in the bifundamental. So they behave quite differently. These two vacua behave quite differently. And for most of the talk, I will focus on the X one, on the second one. So the claim I said I was going to make, and then I had to explain, is that the Hamiltonian, this nearest neighbor Hamiltonian, can be written in like as a sum of some type of dynamical Temperley-Lieb generators. So it can be written in this way, where this upper index is indicating like this index is related to color that we had before. Okay, but to explain what's a dynamical Temperley-Lieb generator, I think I first need to explain what's a Temperley-Lieb generator. So a Temperley-Lieb algebra is defined by these commutation relations. So usually each E will act non-trivially on two sides. And usually we have like a relation for like where these EIs are mapping L Hilbert spaces to L Hilbert spaces. And you see that you have a quadratic relation that basically when you square it, you go back to itself with a coefficient. But you also have cubic relations. And here, you basically, if you do E1, E2, E1, you get E1 again. So if they are close to each other, you get this relation. But as soon as you go more than one apart, they commute. You can represent them. They are very nice. They appear in many things like knots, like John's polynomial, like a lot of, they have very nice structure. And one of the things you notice that you can use these graphical relations for them. You can represent an EI as having this kind of antisymmetrizer. This will be like an antisymmetrizer in the positions I and I plus 1. So it acts non-trivially only on these two sides, and basically identities everywhere else. And the other thing I have to tell you is that this bubble is always a number. So with these two definitions, you can start checking these things graphically. Let's say we are just focusing on three sides just for simplicity now. If I start with E1 and I multiply by another E1, this bubble became the number, like I said before. And so this middle is gone, and what I have back is exactly the same from the beginning. So I can just multiply these things and I get with the pictures the result. And for the cubic, it's very similar. I start with E1, then I put, so this antisymmetrizer is in the first two sides, then I do E2, so they are in the sides 2 and 3, and then E1 again. But basically, you see that if this was thread, for example, I could just straighten this one, and I get back again the same relation. And this, in particular, exactly this one appears in the XXZ chain. And there you actually can write the Hamiltonian of the XXZ chain in terms of these Temperley-Lieb generators. And one thing that you notice is that if you write in the states in terms of symmetrized and anti-symmetrized states, What the Temperley-Lieb does is that it always kills your symmetrized states. So you can just think of like something like antisymmetric times something symmetric 0, like there's a schematic way to think about. But when you act on something antisymmetric, you get this number. So you see, for example, for xz, if you write this kappa antisymmetrized state, and I act with E1 here, I get the bubble again, and I get the state, the same state back. So I forgot to say, yeah, I'm representing states now as this attached, like basically half of a generator of the Temperley-Lieb. And if you have symmetrized, you get 0, always 0. So far, so good. Okay, so so one thing is like, how can I use this? Let's say I want to I start with a vacuum that is all x, but then I want to put one magnum, so I want to put one z. A way I can write my states in terms of antisymmetrized states is like this. I have the one where the antisymmetrizer for 3 sides is like in the first 2 sides, and then in the other 2 sides. If I act with E1 here, it's exactly what we said just a minute ago. You just get the same thing with a coefficient. But if you act with E2 instead, you get this behavior. And then again, you just straighten the line and you get the other one. So basically, this is like a nearest neighbor system. So what the E is doing is either giving the same thing or moving one to the side. Like this case, for example, you start with the bubble here and it went to the other side. So if you do this for this small sector, what you get is this Hamiltonian, that if you diagonalize, it gives you exactly the correct eigenvalues for the xz and the correct eigenvectors. So you can focus in these sectors and use this to solve. And if you do 4 sides, there are some, I just want to highlight some behavior that happens here, which is like singlets and triplets don't mix. So if you do the same tricks I was showing you for these cases, for the singlets or for the triplet, you find a little matrix here that you can solve and a little matrix here that you can solve. They don't mix. This will be important because for the n equals to 2 theories, they will mix. And this will kind of explain the breaking of the symmetry. Okay, I'm going ahead of myself. Let me be a bit slower. Okay, so now what is the dynamical? So I told you that we can represent ours as this sum of dynamical Temperley-Lieb generators. So for the quadratic relation, nothing changes. Basically, we have this index on the top, but we always get back the same coefficient. But now, oops, oh, what did I do? Yeah. Okay, so just for simplicity, let me tell you what happened to the cubic relations just for 3 sides. But something very curious happened here, which is like, let's say we act on a state that has 1x and 2 z's. Remember that before, for xz, the fields were basically up and down. We were calling them x and z, but they were 2 fields with exactly the same nature. Now we have 2 fields that behave quite differently. So here, if you have 2x and 2 z's and 1x, what you get is basically what we had before with a coefficient equal to 1 here on the right-hand side. But if I act with 2 in a state that has 2x and 1z, I get this and I do E1, E2, E1, I get a kappa squared here. And if I do the opposite order, I get a 1 over kappa squared. I will show how these coefficients show up very soon. But basically, in this sense, it's dynamical. Like it cares about what type of fields you are acting on. So, and it gets like, I didn't write the full relations here, but it gets worse. Basically, what we have is like a function here in front for the case with I plus 1i, for example, we have a function here that has an operator inside that counts basically if it sees a z, it counts as 0. If it sees an x, it counts as 1. And then you get some, and this gives you like the powers of these kappas, for example. But okay, so we have this different structure now that splits. And a way to represent this is with colors. I don't know how visible they are. So we are representing here blue for color 1 and red for color 2. And then you have now 2 types of generators and 2 types of bubbles, but the bubbles, as I mentioned, the quadratic relation is the same for both of them, so the bubbles keep giving the same coefficient as before. Now we can start defining states, but there are many, because Z and X behave differently, we have more options to do things here. In particular, we have these like symmetrized states that I will call phi, and the anti-symmetrized ones that I will call psi. And like before, basically, if I act with, it doesn't, independently of this index, if I act in something symmetrized, I will always get 0. So this didn't change. And in particular, in the pictures, you'll see basically like when you have like half a circle with half a square, basically just is just like 0, because it's like when you're multiplying something antisymmetric, it's something symmetric. But then when you act with EI on a state psi, you get basically that number that I told you, the kappa plus 1 over kappa, when this I is equal to J here. So as long as your E is acting on the right index. Otherwise it's 0 again. Okay. So let's say we are studying the open chain with 3 sides. So basically I have, I already put explicit the sides, so sorry, 4 sides. I have E1, E2, E3, and I have the 2 color indices. Okay, if I start with a vacuum, I only have x's, and if I act on and just do x's, as I mentioned before, it's 0. So the vacuum giving me 0. Now, if I put one magnum, I can put it this antisymmetric, like I put the z's here. Always, oh my God, I forgot to say something super important. The color is specifying, like the color here is specifying the first index in each field. So for example, if you have an X here, this is X21, the next color has to change because since this indicates the first index, the next one, like it ends with an index that is different. So I don't think the rest was understandable. Thank you. Because of, sorry for that. But you can put it in these 3 ways. This antisymmetrizer. And then when you act, but then you see, it's a bit confusing how to act. When I act here, let's take the first one. If I act here, it's easy because it just gives me the number, because it will give me the bubble. And if I act here, it will give me 0 because it's symmetric. But how do I act in this middle? So a trick we are doing is basically rewriting the state. You can use some symmetrization and symmetrization, play around, and you see that you can rewrite the state as something that now has the bubble in the middle, but with a different color, plus something that always gets killed by the E. So if you do these things, you realize that every time you need to move the bubble to the right, you get a, doesn't matter the color, you always get the same coefficient. But if you want to move it to the left, if it was a red, you get a kappa squared, and if it was a blue, it gets a 1 over kappa squared. And if you start to act with those generators here, you see how these coefficients on the right-hand side of the relations appear, for example, directly on the state. Like one of the consequences, oh, okay, I was saying, okay. One of the consequences that, okay, so if now I do 2 magnums, if I continue this computation, I do 2 magnums. Now I have these 5 states. So instead of having 3 and 2 separately, they all mix. Actually, each of them mix with the other 2. So you always have like each line has 3 non-zeros. And this gives the correct spectrum in the eigenvectors. We can, if we act on this one, for example, we get something related to these and these. But if we act on this one, we get something related to that and that, etc. You solve these, you get the correct eigenvalues and eigenvectors. But there is a mixing between singlets and triplets. So this basically tells you how the SU2 got broken, like because there is this energy splitting. So I think in this sense, the Temperley-Lieb is already very nice because it shows you what's happening on the break. Okay. And when we go to kappa equals to 1, this should be again like SU2. And there is no mixing, but you can see from this, just from 2 magnus, you can immediately see that for kappa equals to 1, these 2 blocks become 0, and like there are a 2x2 and a 3x3 that don't mix. So you kind of recover the symmetry when you send kappa equals to 1. Okay, what if I wanted to do that n orbifold? Basically, you need to put more colors. Now you sum, everything still works, the algebra still works, but you have more colors. So now you sum, if you have zk orbifold, you sum up to k here. You have now k coupling constants. And the right-hand side of your Temperley-Lieb will depend on all these couplings. Okay. Can I have 1 more minute? One or 2 more minutes, or? Okay. But what is this dynamical Temperley-Lieb? So there is another way to interpret this, which is basically if you take this dynamical Temperley-Lieb and we do a twist that's dynamical, so a twist that like for example here, this f keeps track of how many x's you had before. So if it was an f2, it will see if it was an x or an z in site 1. But if it was like an f5, if you are doing like in site 5 here, it will be like it will be counting how many z's and x you had in the first 5 sites. So this is it's not a global twist, so it really changes every time you are applying. But if you do this twist, something very nice happens, which is you can write this twisted object like this, where each of these t is the standard Temperley-Lieb generators that like the standard Temperley-Lieb algebra that we saw in the XXZ. But each of them with one different coefficient. So if you write the Temperley-Lieb, sorry that I changed it to t here, it's just we are calling both the e's, the both of them. So here, if you take the normal Temperley-Lieb, now with a delta here, but we put a different delta in each copy. So basically this gives something that is the decouple, like n copies of the Temperley-Lieb, or actually k copies of the Temperley-Lieb. And so basically if you start with k copies, or for this two copies of XXZ, like the standard Temperley-Lieb, and you twist in this dynamical way, you get our dynamical Temperley-Lieb. So the whole thing that, for example, you cannot write an R matrix like a standard R matrix, so solution of the Yang-Baxter, everything is caused by this dynamical twist that is messing up. Is a twist that breaks co-associativity, for example, and it's not, it's not a global twist. Okay, I already said that. Yeah, so the summary is that we have a ZK orbifold, like that we have like that is Hamiltonians of ZK orbifolds can be written as dynamical Temperley-Lieb algebras, and that we can obtain these dynamical Temperley-Lieb algebras from L copies of the standard Temperley-Lieb if we twist them in a dynamical way. And what we would like to do in the future is one of the things is computing the coordinate beta ansatz in this basis with the Temperley-Lieb, and try to compare with the results already in the literature in previous papers from Costas and collaborators, and also this long range one from Denise, try to see where this structure is coming from using this. And of course, we only did exact sector here, so it'd be interesting to know what carries to other sectors. And that's all I had. Thank you. Oops. I'll show you the extra slide by accident now.
Joanna, questions? Well, I have a question. But could you show like 17 or 18? Yeah, well, 17, yeah. So your Hamiltonian does not seem to be Hermitian. The Hamiltonian we see here is not Hermitian.
So I think this is just a consequence of the choice of bases that mixes up things in a way that's not standard. So, but it gives you exactly the correct eigenvalues and eigenvectors, which are the ones from so I think it's just an artificial effect from this choice. This choice is very nice to apply the Temperley-Lieb, but it's not the standard choice that you would usually do. So I think this just puts you in a
So if you are just, well, if you don't know the answer, can you kind of determine whether the model you are dealing with is Hermitian or not?
Well, the eigenvalues are all real.
Well, if you don't know, well, if you have a more complicated model and you know, and you don't know in advance the spectrum of this model, can you still determine whether it is a Hermitian or not?
I think you can try to go, like in terms of the Hamiltonian, you could try to go back to just the normal basis, right? You could just try to.
Well, that's basically the question. Can you do it without using the normal basis? Because as far as I understood, this is the basis adjusted to your algebra.
That's a very nice for the algebra, yes.
Right. So now the question is, if you are just given your algebra and Hamiltonian written in terms of this algebra generator, can you determine whether the model is Hermitian or not?
I don't see an easy way except for for computing the eigenvalues, but I understand if it's very big and complicated, that's not the best answer. But so yeah, I think what I would try to do is try to go back to the standard basis. If I had the full one, it would not be impossible. I think that's the easiest.
Okay, thank you.
Thanks for the nice talk. Question. So, in some of those dynamical spin chain types of model, I've never worked with this, but there's somehow a mapping, like vertex to face mapping, which maps the dynamical model onto a non-dynamical one. Could you use this in your case to maybe do a PT ansatz in the non-dynamical one and then map back or something like that?
So this twist, for example, is a bit funny. Like, for example, like usually there you either have like, you can twist it and go back to the on the front one, but usually you either have the twist or the, like, I forgot now the argument, but we discussed this last week, but I forgot now. But we have like, usually there is one thing that you either have like one or the normal dynamical Yang-Baxter, for example, or the standard one, but with the, you can map it with the twist, but we somehow still have like a co-associator afterwards. We cannot, there is something left. We have like two objects, but we can discuss later because now my blanket.
Yeah, okay, sure.
Yeah.
I guess a little bit related, but so you know how the generators of the Temperley-Lieb twist, can you also write a nice relation in terms of the Hamiltonians, the formed Hamiltonians in
Not a nice relation, I would say, because since this twist is side dependent, I have like here, when you write in the way we wrote, sorry, where here, you have just this sum of e's. As soon as you do this these, it will mix, and then you have like the first e will be like just like maybe a t, like the front one, but as you go, like every term will have more things because it keeps track of everything that comes before. So every term gets modified in a different way, and that's why it's not global. And so that seems a much more elegant kind of description, but at the same time, this one seems more like at the level of the Hamiltonian, it looks much simpler. So I don't know. We don't know yet very well how to use this connection between the XXZ directly to compute things because it's a very recent result.
It might be possible in the end, but maybe you need to work.
Exactly.
Relations.
Yeah. This part, this mixing, like it's very recent result. Yeah.
Questions? Okay, let's send Hannah again.